These notes are for 4.6, and it's really similar to the 4.5 notes. There's just the second part is going to be a little bit different, but the first part will be similar. I'm not sure we're going to get to the Descartes rule of signs. I might do it as a bonus or something. So 4.6, the fundamental theorem of algebra. I know you've been taking algebra for a year and a half now, but you are going to learn the fundamental theorem of algebra. It's pretty simple. And use the fundamental theorem of algebra to determine the number of zeros a function has, a polynomial function. The second half, we're going to find the conjugate pairs of complex zeros of polynomials, which I've already hinted at in the 4.5 part 2 notes. And if we get to it, we'll do the Descartes rule of signs, which is kind of cool for figuring out how many types of different answers you're going to have. So here's the fundamental theorem of algebra that you've all been waiting for. It says that if a polynomial, f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has at least one solution. Those are the roots, right? The roots are the zeros. One solution in the set of complex numbers. Now, remember that if you have 0 or 5 plus 0i, it's still considered a complex number. Complex numbers contain all of the real numbers. So complex numbers, it doesn't mean that there doesn't have to be a complex solution. It just means that all the numbers will be either real or complex. Okay. And the corollary is that if the equation has repeated solutions, then those count towards the number that you have. So if a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has exactly n solutions, provided each solution repeated twice is counted as 2 solutions, or if it's counted 3 times, it's considered 3 times, and so forth. So we'll see that, and I think we talked a little bit about bouncing before, so it's going to be similar. A lot of you are going to like this because I'm going to use Desmos for a lot of it so that you can see how that works. So anyway, how many solutions does this equation have? X cubed plus 3x squared plus 16x plus 48. Well, I think that the highest power is 3. Therefore, we would say that it has at least one solution, but it could have up to 3 solutions. And that's what the fundamental theorem of algebra is telling us. Let's see if that's the first one that's graphed or not. I guess not. So they were just saying, well, okay, well, how many solutions is that? Well, up to 3. That's what the answer is. Up to 3, because the 3 is the highest power. And it didn't say what they were. It says how many does it have? Well, it's up to 3. This one, how many zeros of the function? Well, up to 4. There could be up to 4 because the highest power is 4. Doesn't mean there are 4, but there could be up to 4. So I don't think that's the one I did either. Yes, I did. So what I want you to notice about this is the reason I didn't do factoring by grouping on this one is because if you look at the ratio between x to the fourth and 6x to the third, that's 1 to 6, but 12 to 8 is in a completely different ratio. So factoring by grouping didn't work. Although I could divide out an x, certainly. I mean, we could do this by hand. We could take out an x and see what's left, right? We could say, oh, that would be 6x squared plus 12x plus 12x plus 8. And then we could say, oh, well, factors of 8 and go through 1, 2, 4, and 8, positive and negative. We could get it synthetically that way. I just thought that I'd want to show you a combination of using the Desmos and using the other methods that we've already learned. So let's take a look and see what Desmos has to tell us about those zeros. Now, if we look at this thing, it looks like, this is the first one, it looks like it crosses the axis at -2, and it crosses at 0. Well, I knew it was going to cross at 0 because there was no constant, but the question is whether this represents 1 or 2 answers. But the reason why I'm doing this is because if we're going to find them, that's real helpful. Well, the 0, I think that, like I said, I think the 0 is more obvious because we have a common factor of 0, right? 12x. Sorry. 12x is only to the first power. This one's to the second power. Second power, first power, and then the 8 is common. Now, then we just saw that -2 is one of our answers. So we could go through and do this synthetically and figure out what that other thing is. So for instance, 1, 6, 12, and 8, and -2 was a 0. We saw it on the graph, so we know it's going to work. -2 times that would be -8. There's our 4, -8 again. So that tells me that I've got x and x plus 2, the x plus 2 because of -2. And then this would be x squared plus 4x plus 4. Wait a second, what's going on there? X squared plus 4x plus 4 factors, doesn't it? In fact, we know that that factors two numbers that multiply up to 4 that add up to 4 would be x plus 2 and x plus 2. So this is an example of -2 being the answer 3 different times. These are 1, 2, 3, and then this one's our 0. That's our other answer. Therefore, there are no complex answers, and there's no imaginary answers. There's only 0 and -2. Even though there are 4 solutions, that's because the -2 gets counted 3 times if you want to be official about it, right? So that's an example how the graph helps us. We couldn't see that it was a triple root on that one, but when we factored it by hand with that information, we could tell. So here's another one, x to the 5th power and this whole mess. And let's see what Desmos has to tell us for this one. I think I grabbed it over here. I'll put it in ahead of time. Okay. There it is. All right, so that x to the 5th thing, it looks like the only answers that we can get from the Desmos are at -1 and 2. So I'm going to use that information to do synthetic division. I'll do it with -1 and 2. By the way, both -1 and 2 go into 8 like they're supposed to. So we're not, shouldn't be really surprised there. Remember to put the 0 for x to the 4th. 1, -2, -12, -8. And what do we say it was? I've already forgotten. -2? Was it -2? I hate to go back. Well, I guess we'll find out. Short-term memory problems, I'm guessing. All right, let's see if this works or if it was +2. I've forgotten. -10, -12, +24. Yeah, I guess it's no, I guess it was +2. You guys all knew that. All right, so +2. It better work now. All right, well, +2 and -1. All right, so this is 2. 1 times 2 is 2, usually. 8, 16, 4, 8, and 0. Okay, so that was right. And then the other one was at -1. So I'm going to keep on going from here. I can do it in another color. 1, -1. Let's see, 1. That's +1, by the way. Just a little fluke. 1, -1, 4, and -4, 4, and -4, 0. All right, so now I'm left with 1, 1, 4, 4. This represents x to the 3rd power plus x to the 2nd power plus 4x plus 4. Now that looks a little suspicious to me. Those are in the ratio of 1 to 1 and 4 to 4. So I think that I can continue with this by factoring by grouping and see what happens. But it looks to me, if it's in the ratio of x plus 1, I'm guessing that -1 will be another answer if I want to figure out what's happening here. Let's just see if that's right. 0. That was a 4. No, it doesn't look like it. -4. Yes, that was x. Another -1. Did you notice on the graph how it bounced at -1? It bounced at -1, and that's why there's 2 roots there. So I'm left with x squared plus 4 equals 0. Now I can get the last answers. X squared plus 4 equals 0. So x squared equals -4. taking the square root, I'm going to get plus and minus 2i. They're conjugate pairs that are imaginary. So we can't see those on a graph at all. Just the 2, -1, and plus and minus 2i. Now, the reason why there are 5 answers, because the highest power is 5, if you count the -2's twice, right? So there we go. Find all the zeros. Well, we did. All right, let's see another one. How many zeros does the function have? Up to 3. That's all there is, up to 3. Let's see what they are. Let's see if the Desmos will tell us what they are. Get it out here. It's this one, I think. There it is. Oh, that doesn't look like anything, does it? Looks like it's going through not anywhere pretty, right? -2.097. That's not really helpful. What in the world is going on with this thing? Looks like it only has 1 0. If I just keep on going out and out and out, it's only going through the x-axis at one place, somewhere left of -2. So those would be that would be a tough one to find, because I don't know that we have the right tools to be able to do that, but it's not going to be a rational number. So none of the rational answers work, but I can tell by looking at the graph that there's only 1 0. So there's one that's going to be an irrational number, like whatever that was, or irrational number, and then there's going to be one that's going to be there are going to be 2 that are going to be imaginary. I imagine we could use Descartes' rule of signs to find that out. So it didn't actually says find them. It said how many are there. This last one here, I think this is the last one. The last one here says find all the zeros. So let's do it again using our friend Desmos to find it. Let's see. Here it is. Put it in there. Looks like it bounces at +1. So I'm guessing there are going to be 2 at +1. And it looks like there's one at -1. So I think if I do synthetic division twice with 1 and once with -1, I think I'll get it down to something reasonable. Let's try that. 2 at +1, 1 at -1. I'm going to remember this time. All right. 1, -3, 5, -1, -6, and 4. Let me just double check. I didn't lose anything. 5, 4, 3, 2, 1, 0, 1, 2, 3, 4, 5, 6 terms. -3, -1, -6. Okay. And we said that there's going to be 2 of them at 1. Let's try that. I think that's because it's bouncing. So let's see how that works. We should be able to narrow this thing down quickly. There's the first one. I'm going to use 1 again because it bounced. So 1, -1, sorry. -1, 2, 2, 4, 4, 0. There we go. And then we're going to use -1. And we're left with 1, -1, -2, +2, 4, -4, 0. So what I'm left with is, this was x to the 5th, x to the 4th, x to the 3rd, x squared minus 2x plus 4, and that doesn't factor. So the question will be, if we wanted to find the last 2 zeros of the polynomial, well, they'd be roots of the polynomial. If they don't touch the x-axis, I call them roots. If they are touching the x-axis, I would call them zeros. So x squared minus 2x plus 4, x squared minus 2x plus 4, I think the only way I could solve that is using quadratic formula. Let's see how that works. The opposite of b, plus and minus the square root of b squared, minus 4 times a times c, which is minus 16. That's why we're going to get an imaginary number, all over 2 times 1. So I'm going to have 2 plus and minus the square root of -12. This 4 minus 16 is -12. So that would be 2i radical 3 all over 2. So the other two answers are 1 plus or minus I radical 3 and over 1, which is just going to be, I don't need to write it, over 1. So those are two of the answers. The other answers were -1 and +1. Those are the places where it crosses the x-axis. Those are what I'd call zeros. These other two, these conjugates, I would call them roots because they don't touch the x-axis, but they're still solutions. They're all solutions. So in this case, the roots, zeros are all roots, but not all roots are zeros. Zeros are something I can see on the x-axis, and they're roots also, but some of the roots don't touch the x-axis.